Okay, let's get to a real PDE and see what the connection to this all is. What are you seeking? Well, here I started off, he has a lot of examples with 3 variables in it, but I think 2 variables illustrates it so that you can actually see the pictures at the very end. So what you're seeking is a function. Just like an algebra equation, you're seeking a number. With an ordinary differential equation, you're seeking a function of 1 variable. Here you're seeking a function of 2 independent variables that satisfies this equation. So the first step is to set up what's called the characteristic equations. So this is the how-to, this is not the why. And what you'll do is you'll set dx over 1, dy over 3, and du over 0. Don't let that freak you out. This is the way Zachman and Glo does it. It's not the way everybody does it, but he tells you to calm down. It's not a real division by 0. What turns out is that this number that you put here is the coefficient of ux, and it could be a function. And here you have the coefficient of uy, and this is the coefficient of u, which there is nothing in there, so you put 0. And then you form solvable equations by cross-multiplying. So for example, I could take dy over dx is equal to 3, and I could take du over dx is equal to 0, and solve these equations. So I'll get y is equal to 3x plus c1, and u is equal to c2. And then I'll isolate the constants. So I get the c1, a formula for c1 and c2. Now c1 and c2 are related. I'm going to tell you why a little bit further on, but they're related by a function. So you set c2 equal to a function of c1, and what you'll find is that c2 is equal to f of c1, and substitute what you know about c1, which is y minus 3x. So these constants are not unrelated, they're hooked by a function, and that function is general. And if possible, if that c2 wasn't alone, you're actually trying to solve for u. Or you can leave it implicitly if it shows up in a messier equation. This was a very simple equation, so you didn't have any u's squareds or anything hanging around. But if possible, you will solve for u. In this case, we just got it because it was the simplest thing I could write. So we get u of xy is equal to a function of y minus 3x. And that seems very unsatisfactory, because what we're used to is getting an actual function like x squared plus y squared. And we didn't get that. But that's because just like you have a constant of integration when you have a one-dimensional ordinary differential equation, here you have a class, a family of solutions that are all functions. F could be any function. So it's called a general solution. And any f will work. So let's check it. If I just take the derivatives, ux is going to be the derivative of f times the inner derivative, the chain rule. So this minus 3 comes from chain rules. To find ux, I take the derivative of f, and I multiply by the inner derivative of the x term. And uy would just be f prime of y minus 3x. If you stick these things back into the equation, what you find is they do in fact total up to 0. So, and any f would have done the job as long as it was c1. So that was the punchline that he's getting to. And I think also when he's building up this theory behind it all, he's also very careful to show you criteria that will guarantee you existence of solutions using this method. So he talks about what's called independence of functions, and he has a cross product. So there's some theorems in there that are pretty important, but what I'd rather do is go back and draw upon that as we need when we are worried about existence of solutions. But it is important, I don't want to discount it. So why does C1 equal f of C2? Well, it's because the equations are all related to each other. They're just not, it's not this dx over something dy. They're all 3 in tandem related to each other. So the C2 came from one of the equations that you had that were all equal, and the C1 came from another one. So you can actually derive this dependency by going back and resubstituting and playing around with them. So they're hooked together. They're not independent, non-connected equations. They're connected to each other. So what if they give me more information? What if they give me what's called the initial data? So in this example, I gave you the example before of the table being a sheet of metal and the flame underneath it. It's kind of easier to understand that 2D example, but we don't have a 2D example here. We have a 1D example. So you can think of y equals 0 being right here, and y stretching out, and think of x being time, and think of some concentration of something. I don't know why in the world I thought of bugs, but think of like some concentration of a population or a density inside this tube. Then as you move forward, there's going to be some initial spread of that density throughout the distribution of that density throughout that rod. So for example, maybe there's more bugs over here than here. So you have some kind of numbers at a function. And that function is given, I'm just making it up, I would just put y squared there. So that tells you what the initial distribution is going to be. With that distribution, there's 0 bugs at the beginning of the rod, and there's more bugs as you go along the rod. And then you apply that initial data to solve for f, just like when you were in Calc 2 and you applied the initial data to get rid of the arbitrary constants. It's the same deal. So if we do that, we plug in x equals 0, and we get only a function of y here left. And that function of y is supposed to be y squared. So that tells you what f is. And that gives you now as a very specific solution. So now that's satisfying. You have the actual formula in your hands. But you're not going to get that in general. You're going to get what we call the general solution, which has an arbitrary function in it.